you can see some general information about our so-called text-to-tech project. We are 3 project participants, and yeah, the project has been running since May last year and will continue until the end of April 2025. And yeah, the project is funded by the German Federal Ministry of Education and Research. In general, the project goal is to develop automated methods to automatically identify technologies and its relations in unstructured text. So that's what what's the term text-to-tech means, transforming text to technologies. And today we will propose 2 approaches. The first one is a classic fine-tuning of pre-trained transformer models, and the second is what we call prompting and distillation. And after the 3 years duration, the results will be, of course, the fine-tuned models and a web application as a demonstrator where you can try out the capabilities of the model. And when I mentioned a couple of times identifying technologies or technological concepts, is the question, what exactly are technologies in our understanding? And yeah, here I will hand over to David.
Thank you. I will talk a bit about named entity recognition. So what we have in the project are documents. These documents come from different sources. I'll talk a bit about that later. And what we want to do is identify technologies within these documents. And yeah, the task is defined as named entity recognition, which is we want to detect spans, so single word or multiple word spans in a text, and we want to classify them into different entity types. For our project, we decided on 4 entity types, some of which are already are sometimes seen in text, but usually, like, these are unusual types at least. So material is easy to understand. It's just basic input. Method is the process of transforming something, usually taking materials. Technological systems are everything that is produced, artifacts, and technical fields are the domains or buzzwords that are operated in. And if you look at the sample sentence from a document, you see all 4 entity types present. Photonics and telecommunications are technical fields. An optical amplifier is a technological system. Amplifies is a method, and light is a material. And in addition to those 4 entity types that we want our named entity recognizer to detect, we currently use SPACY to detect organizations, because later on we also want to identify which organizations work on or are related to which entities that are mentioned in the text. So how do we get to the labeled data that we need to train a classifier? We take data from 3 different sources, from news reports, scientific publications, and patents. Those are all already filtered or specially selected with a focus on technology. And then during the first stages of the project, we iteratively developed an annotation guideline to determine and distinguish the entities. And yeah, we did that both with linguistic experts, but also domain experts. So for our current data set that we are using, we have the following statistics. We have 2 types of documents, full text and abstracts. For the annotated data that we have in the training set 100 full text and 100 abstracts and 10 documents for validation, and an overview over the number of entities that are present in these documents is that in the train documents we have around 1,000 technological systems, around 500 materials, 200 something technical fields, and around 100 methods. And in the validation documents, which are of course a lot fewer, we have around 70 technological systems, 40 materials, 20 technical fields and methods. Now we want to actually train a model on this data and see how well it does. We train a language model classifier. We use XLM Roberta on the 200 training documents, and then we evaluate on the 10 documents. And we have another approach, not only fine-tuning a classifier, but also few-shot. That is an existing setup, using an existing setup that we have. And for those, we only take the 10 validation documents, so the training documents are not used. And then we split those into support documents and query documents. Each support document is only used for one class, which means we have 4 documents used for the 4 entity types, and then we use the other documents for querying. And then, yeah, the output of the language model encoder is used to classify, and we run 600 iterations to basically eliminate chance of how well specific documents support, or the entities in specific documents support specific classes. All right, those are the current results that we have. All of the scores that you can see here are micro F1 scores on a token level. So we just classify tokens, meaning is this token, does this token belong to a entity, and to which entity, or does it not? And as you can see here, we have overall results of around 0.4, 0.5 micro F1 score. That the fine-tuned model has a bit different results for the entity types than the few-shot model. This may be both to difference in documents for training and validation, but it also may be due to the different approaches. For example, the technical system is much better detected by the fine-tuned model, whereas material, for example, is much better, is detected much better by the few-shot model. Overall, we consider these results promising, but not as a good final result. So this is not comparable to results that you get on, let's say, standard named entity recognition datasets. We are aware that our task is obviously more difficult as we are dealing with harder entities, harder to distinguish entities. But yeah, we are regardless quite happy that we get decent results so far. And then I want to give a little bit of an outlook. I alluded to the fact that we also want to do relation extraction, because to us, to the project, the relation between organizations and their technologies are interesting and relevant. These relations are unfortunately difficult to detect, because unlike named entity recognition, we can't just look at single sentences to determine whether a relation is there between an organization or and a technology, because the relation can span over multiple sentences. An organization can be named in the beginning or end of the text, and the technology, relevant technology, can be somewhere else in the document. So what we're currently doing, and what Jan will get to in more detail in a bit, is that we're prompting large language models, for example, ChatGPT, to produce us output that detects this basically in one go. I can allude to a sample in the next slide, where we have organization North Carolina State University, or also called NCSU, and we want to find out which of the technologies that are mentioned here are relevant for that university, or which does the university actually work with. And then we take this input text, we give it a prompt, and then we get an output of where the model tries to explain and show which technologies are relevant for the organization. That's just a quick look into the future of what we want to do. And now Jan will get into the details of how we do prompting.
Okay, awesome. Thank you, Felix and David. I'll take over and speak a bit about prompting and distillation. So what in fact is different here is that we're using large language models in a GPT style, so a generative LLM, instead of the encoder approach as it is done in the Roberta experiments. And there's also one important aspect to keep in mind before David introduced the documents and the way of how we label them. And all of this, of course, in these experiments is not used. So what we start with is a set of documents completely unlabeled. And then the prompting is a zero-shot approach. And distillation will try to incorporate that what we've learned through prompting and through maybe some manual labeling into a distilled open source model. So first of all, why do we look into this? David already mentioned a few of the problems. One of them is that our task, our problem is very hard to define unambiguously. So in some settings, a technology could be, I don't know, a laptop or something. Yeah, let's say a laptop, and it could be the technical system that the document is about, and that it discusses its advancements. But it could also be just a tool to show something, to show a graphic or something, so noted in a different way. And then we also have the problem that it's for us really hard to define strong or good guidelines for the labelers that they can use and have high agreement with each other. And therefore, what we hope is that the world knowledge, so to speak, of these large language models can be used to tell them that we are looking for example, technical systems, and they will understand in a way. And then we have another problem that is that labeling in itself is tiresome, and it needs expert knowledge in a broad set of domains. And one way of incorporating incorporating large language models is to help us do the labeling process more efficiently. You see one of the examples here, the upper box with the text: the propagation of excitation along a one-dimensional chain of atoms is simulated by means of NMR. And then the question is, okay, what is NMR? And in fact, you don't see the entire text here, but it is not mentioned anywhere else in this abstract. So the reader would have to be a domain expert and know what NMR is. But if you prompt it, you immediately get results like, okay, it is discovered as an entity, and it's explained as nuclear magnetic resonance. And of course, it is much easier to just check whether that makes sense, that finding, than to actually do the research, find the right term, and then label it yourself. So this speeds up labeling by quite a bit. And then we have another problem we're facing, or a difficulty, that we need to edit or summarize entity names in sometimes. Maybe we look at the other example here with the sentence that convert carbon nanofibers and nanotubes into and here we could, in the classical approach, only detect carbon nanofibers and nanotubes, but with the generative models we can basically extract carbon nanofibers and carbon nanotubes. And one last point regarding the motivation is that we can use it to perform relevance filtering much better, as they have like what technical system is actually relevant, because they have a better understanding. Now let's look a bit about into the approach we're doing. Here's an overview. You basically see two cycles that are connected by the generation of a model in the middle. We start on the left with prompting. This is a basic prompt engineering task, and what we also do is we define an output structure. That output structure could be a list, or in our example, it's a JSON file. And then what we do is we start a first cycle of guided generation, and for guided generation, we use OpenAI's function calling in a first run, and then later on we're using a templating method which only allows certain tokens at certain positions, so that we can ensure that our output definition from the previous step is matched in all cases. And then we go down the circle and evaluate the output. That has to be done manually. And then we either go back and tweak the prompt a bit, or once we see prompt engineering doesn't improve the system anymore, we turn to the right and manually edit the output. So maybe changing some descriptions, correcting some classifications. And based on that high-level training data, we then fine-tune an LLM. Currently, we're using the Llama models and train them with the QLoRa approach. And then again, we do the guided generation and hopefully increase the quality step by step. And then a last slide about the evaluation. An evaluation about the entire approach. So what we can see, and I showed it in some examples, that we're actually using the world models or the contextual knowledge of the in the pre-labeling, and we actually see that it reduces the necessary training examples. With only 200 labeled documents, we already get quite good results. The models quickly learn to capture the output structure. When we fine-tune it, we even don't need the guided generation or the templating after one training loop. And we also see the capabilities of rewriting entity names or coming up with names, for example, in patents. The disadvantages are, of course, that the processing time is quite long when you use a larger, like 70 billion parameter model. And evaluation is tricky, especially because when you rewrite entity names, for example, you cannot have a gold standard you can match to. And then as an outlook, what we are trying to do and already see quite good results in is combining named entity recognition and relation extraction in one single pass. Okay, that's it from our side. Thank you, and feel free to ask questions.